All right, should we get started? Okay, my name is Collin, and I work as a senior engineer at DICE. And today I will talk about our new culling system that we implemented for B3. So first, some background on how the old culling system worked and why we decided to rewrite it. Then I will go into some of the requirements for the new system, and I will also detail a bit about the target hardware, which we are targeted for our system. Then actually going into some more into details, how the code was implemented and how the data layout was structured and things like that. And as well, I will go into our software occlusion scheme that we are using to even cull even further. And in the end, just have some conclusions. So, first, an overview of the old culling system. And the old culling system was based on a hierarchical sphere trees. So we have first one static cull tree that was generated offline. Then we had the dynamic cull tree that was updated in the runtime. And here's an overview of how the tree looked like, and this is pretty much the same for both the static and the dynamic one, except the static has a bit tighter layout and was pre-computed in a pipeline step. So this works it's a pretty classical sphere tree where you see if you're inside one sphere, then you just recursively traverse down the tree to see if you find some visible objects or not. So, why did we actually decide to rewrite the system? Because we had actually used this system for 4 shipping games. And one of the reasons was that in B3 we wanted to add lots of more objects, more dynamic objects. So we are running into scaling problems with the dynamic cull tree because you are adding lots of more dynamic objects into it. And another really important part was that we were introducing a concept of sub-levels, and that means that we can now stream a portion of a level into memory. In our earlier games, like Battlefield 1 and 2, for example, we had all the levels in memory. So this added some extra complexity to the new system, and the old system wasn't prepared at all to handle sub-levels. And it also caused a problem with the pipeline because we had to build separate trees for the sub-levels, and it really didn't fit at all with our old model. And another problem was that it was hard to scale, and we were running into scaling issues with the static as well because we wanted to add more stuff to it. And that was also part of that we were running one job per custom. And I will explain this a bit here. So what we have first is a job graph where we run our culling jobs. So here's an example of when we have 4 jobs. So the first job we are running is the dynamic job. And in this example we have 3 frustums. It's the shadow 1, shadow 2, and the view frustum. So first, this job just collects and finds all visible entities, and for the dynamic entities. Then we run another job here at the same time, and this one is for shadow 1, for example. And the shadow 1 frustum outputs a bit mask. The bit mask is a representation of which objects that are visible inside this frustum. This is outputted, and then we also start a bunch of other jobs, and then also outputs a bit mask. Then they have the view frustum, which as well outputs a bit mask. So this bit mask needs to be used for something. So in the end, we run a merge pass, which actually takes this bit mask and creates outputs that looks like this, meaning that we need to merge all these bit masks together because the rendering expects to have one value per object of which frustums the object is visible in. And as you can see here, there are some gap after job 1 and job 2, and this is a scaling problem before us, because we can't really use the full utilization of both SPUs and regular cores on 360 and PC. So this was something that we wanted to improve in the new system as well. So we had to look at the requirements for the new system, and of course we wanted to scale better, have more things in the world, so we could scale better. And the new system, as the previous one, needed to support destruction, because in B3 we have lots of destruction going on, same as the older games, and of course wanted to scale that even further. And another thing that we focused on in Frostbite 2, which is the engine that runs B3, is to have more real-time editing, so we could move things around much easier in the world. And if you could have a system that supported this even better, that it will be really benefit for us. And as always, when you want to refactor a system or rewrite something, you want to simplify the code, make it simplified. We also wanted to unify the subsystems, meaning that before we had different code for the static objects and different code for the dynamic objects. So we wanted to see if it was possible to run one system for both dynamic and static. Then, of course, it's really important to know which target hardware we are targeting. In our case, it's PS3, 360, and PC. And in our case, PC is always multi-core, at least dual core, but I would say in most regards we have quad core and above. And knowing which hardware you are targeting, it's really, really important when designing a new system that is heavy like this. So, when looking at these systems, what doesn't work well on them, you need to see what kinds of CPUs we have and what runs good and bad on them. And one thing that's bad on all these CPUs is non-local data, meaning that not reading from the cache is always expensive. So we always want to have local data. This is really important for all the platforms, especially on the consoles. And the branches are really expensive as well, especially on the consoles as well. But we can get things even faster on the PC if we can reduce the number of branches as well. And this is a console-specific thing that is actually really expensive. Is switching between register types. If you need to use a flow in a vector register, you need to write it in memory and read it back, things like that. And what we saw is that tree-based structures are usually branch-heavy. So we started looking some structure that was easier and didn't rely on a tree-based structure. And as always, data is the most important thing to address here. So we were looking at just how could we make the data flow easier to reduce everything that is a problem on these CPUs. So what does actually work well on these systems? Well, if we have things in cache, we can do things really, really fast. And that goes for SPUs as well. There you have to DMA data into local store, but if you have the data layout simple, things get much easier there, and it scales really well to the other platforms as well. Another thing that we have lots of in all these systems is computing power, especially SIMD computing power. The SIMD is really good on all these systems actually, especially on the PS3, but also on the 360 and the PC. On the PC we are targeting SSE2, but that is sufficient enough for this. And of course we have parallelism. We have always multiple cores, and of course the new system needs to take advantage of that. So the new Culling, we expect that simultaneously in our worlds we have around 15K of objects at the same time, and that is pretty much what we looked at when we designing this new system, because it's really important to know if you have 15K objects or 150K when designing a system like this. In our case, this is usually around the maximum number, so that's what we try to work on when we decided to rewrite the system. So the first try was just to run a parallel brute force, doing nothing at all. Just put everything in line arrays and just brute force it. And this turns out it's actually 3 times faster than the old Culling. So that's pretty good. And also the code got reduced in 5th size, which is really good as well. And it's actually easier to optimize even further, to make it even faster. So the conclusion is that this is what we do actually. We use strictly linear arrays and just brute force them. Because we have predictable data, it's really easy to prefetch, things like that. We get really few branches. We just have some loops looping over all data, which makes it really easy. And it uses the computing power of the machine, because you can stay inside one loop doing lots of stuff, just traversing through all the data. So if you're looking at a comparison with the old Culling, the numbers here is a bit hard to read, but they aren't that important. It's more important to look at how the scheduling actually look like. Here you can see the purple one is the dynamic Culling, which is kind of expensive in this test. So if you compare it to the new Culling, it looks like this instead, which is way nicer. And this is actually doing both static and dynamic objects at the same time now. So this is pretty much how we do it. Then, of course, we need to look at some performance numbers. So this is a test where we actually have 15K spheres in the world, just doing actually the same thing that I described earlier. So on the 360, this takes 1.5 milliseconds for one job, and 0.52 when you're running 4 jobs. As you can see here, the scaling isn't perfectly, and this is because on the 360 you have actually hardware threads and not CPU cores. You have 3 CPU cores, but they have 2 hardware threads on each core, meaning that it won't scale perfectly on there, but it's still pretty fast, and this code can be optimized even further if needed. Then we have PC, and in this case it's an iCore 7 with 2.66 gigahertz, and one job taking 1 millisecond here, and 0.32 when running 4 jobs. As you can see here, the scaling is a bit better on the PC. And then we have the PS3. It's 0.85 milliseconds when running 1 job, and 0.23 when running 4 jobs. As you can see here as well, that the scaling is the best on the PS3. This is simply because the SPUs are really independent of each other and can run pretty much simultaneously without getting in the way of each other. Then I also implemented a SPA version, which is even faster on the PS3, which I will go bit more into detail a bit later. So the details of the new Culling. So it's even possible to improve the performance even further with having a simple grid. And what a simple grid really means here is that we have an axis-aligned bounding box that is assigned to a cell with spheres. So it's actually no magical structure at all. It's just we have them inside an axis-aligned bounding box, and then we can just arbitrarily place them in the world to just check if we're inside this axis-aligned bounding box. Then we only need to check if you're inside this, check for the spheres inside that one. And we have in BF3 we have a bunch of separate grids for rendering static and rendering dynamic. The reason why we have it like this is that we have some physics and some physics data, and so that's for static and dynamic as well. And the reason why we have it like this is because usually the rendering system is always asking for rendering-related objects, while the gameplay system is always asking for physics-related objects like soldiers, vehicles, etc. So this is just an optimization, but the structure of the grids or the cells here is pretty much the same. We just have different versions of them, and when we are adding objects, we just decide on the type of object where we should place them. So this is the data layout. This is actually the entire data layout, how it looks like for the grid. So first we have an entity grid cell, which has an array of pointers to blocks. In this case, we have 256 pointers. We have 256 counts. That is count for each block on how many positions or spheres there are inside that block. We have separated this because it requires less memory and things like that. And each cell has a bunch of blocks, and the block layout is quite simple as well. So we have a layout, and there is first the positions is 64, and then we have an entity info. There are 64 as well. And the entity info here is pretty much just a pointer to a handle that gets passed down to the system that's doing the request of the query or the Culling call. Then we have the transform data. The transform data is actually used depending on various circumstances when we need to do some even finer culling. The first pass we have usually doing just frustum versus sphere, for example. Then we only need the position. So it really makes sense to have the transform data separate, because we don't touch that data at all. But the positions we are always touching in some form. So when adding objects, this is actually really simple. We just pre-allocate one huge array, and then we just do an atomic add to allocate from it, which is just a pretty much incrementing a pointer, which is interlocked, and it's just really simple, because then we can actually allocate memory from the SPUs by just moving this pointer forward and filling it with stuff. One thing that might be a problem when adding objects is if you have a layout that looks like this. We have cell 1 or cell 0, cell 1, cell 2, cell 3. They are close together, and if you add one object like this, it would end up in cell 0 and cell 1. The problem with this is that it will be in two cells, and if you're doing a culling that would include both cell 0 and cell 1, we will need to filter out the objects that will be in between. But there's a really simple solution for this, and that is to have an extra cell that just wraps all around these cells, and we just move the object over here. And when we are doing a query, we just simply check check if anything is present in cell 4 as well, making it really easy. One potential problem with having it like this is that if you have lots of objects on the edges of each cell, lots of objects will end up in cell 4. But in practice, this is never a problem. And if it would be a problem, we could simply just move the cells around a bit, things like that. And for us, it's never been a problem, at least. So when we want to remove objects, this is also really simple. We can simply use the swap trick. And what I mean by that is that the data doesn't need to be sorted. So we can just swap with the last entry and decrease the count. So that's really simple when removing things as well here. You don't need to update some tree or things like that. You just need to swap and decrease the count, and you're done. So if we take a look at the rendering culling. So this is the data that the rendering actually expects to get out from the culling. And it's actually quite simple data. This is just the structure, and this is actually how it looks in the game. So first we just have a handle to an entity, and handle is usually a pointer to something that just gets passed down. The culling system doesn't actually know anything about this. It's just being passed down, and the system that wants to have this data just can do whatever it wants with it. Then we have a bit mask here with the visible views, and that's it's a bit mask of which frustums this was culled in, and which views it's actually visible in. So we just have a bit mask telling that. The class E and the screen area here is mostly for performance reasons. So when the rendering system gets this data, it actually doesn't need to look inside the entity. It can look in this data because it's usually always in the cache. So here's actually how our culling code looks like. This is pretty much everything we have in a high-level sense. And this is not exactly how it looks like, but pretty much. So the first thing you do is just find out which block we are supposed to call in, and this we just do with an interlocked increment on an index. To find out which block that we are supposed to process. Then we set up do some setup, clear the masks and things like that, and just take out the block that we're going to iterate over. Here we are simply just looping over the data, doing the intersections, and just merging the values between the fours and things like, and so on. So this is pretty much how the loop looks like in our code as well. Then when we are done going over all this data, we can simply just decide what we want to do with it. So if mask here, the current mask is 0, it's not visible in any views at all, meaning that we can just skip it or create a new list that is filtered depending on this data. So here's an example how an intersection code could look like. And what you should do is, when you see some code that looks like this, you should do like Mike Acton and be like this. So you can look at into Mike's a bit rantish thing about this, and it's really good. You should check it out. I will do my own smallish version of it. So looking at the code again, there are several problems with this code running especially on the consoles. On each line, we get a load hit store because we need to transform the position to float and back and forth for each line here. So we get load hit store, and then for each line we have a float branch, which is as well really slow. Branches are slow, especially on the consoles, but slow on PC as well. So this looks, well, really bad. So the console gets really sad. So we shouldn't do it like this. So, but what can we actually do to improve this? There are actually several ways we can do to improve this, but the thing is that dot products, as we saw here, are not very SIMD friendly. The problem is that you usually need to shuffle data around to get the result. And yeah, I guess you all know how the dot product looks like, but it looks like this. And first, doing the multiplication is actually really simple. That can be done in one instruction. But when you need to actually do the addition, you need to shuffle around to get it in each step. And that gets really slow because you actually can't use the full computation of the machine by doing it like this. So what can we do to improve this? We can rearrange the data from arrays of structure to structure of arrays. And by that, I mean that if you have some data that looks like this, we can rearrange it so it looks like this instead. And if you have the data that looks like this, it gets really easy to do dot products because we can just need 3 instructions to do 4 dot products. And it's like multiply, add, multiply, add, multiply, add, and then we are done, which is much, much faster than before. So we, of course, want to use this technique to improve the performance of the Collin code. So what we do is we rearrange our frustum planes. Typically, when you have a frustum, it looks something like this. So what we do is that we rearrange them to looking like this. So this is a typical structure of arrays array. So first we have x0, x1, x2, x3, y0, y1, etc. And then we have x4, x5, x4, x5, which looks a bit weird, but I will come into a bit of detail later on why we have it like this. So the new intersection code, how does it actually work to improve the performance? So in the loop that we have implemented, we are doing 2 frustum versus sphere intersection per loop. And the reason why we want to do that is to have 12 dot products with 9 instructions. Meaning, because when doing a test for one sphere, it's 6 planes, meaning 6 dot products, and we can do 12 dot products within the loop. And then we just loop over all frustums and merge the result back like you saw before. So, looking at the new intersection code, first here it's simply we're doing a shuffle. And position A here is the first sphere. Then all we need to do is then to do this piece of code to do 4 dot products. And this is for the 4 first planes, in this case for the position A. Next piece of code is for position B. It's pretty much identical to the previous code. Just shuffling out so we can do the dot products really efficiently, just doing splat of each component. Then doing the dot products here again. Now we have made 8. And then here is the last 4. It's a bit trickier, but what we do is just combine position A and position B. And then we can do 4 dot products like this. And here is why we stored like x4, x5, x4, x5 for the frustum. And then the last part is simply taking all this result and merging it together to see the final result. So first we just do the comparison to see if where the radius was, if it's actually inside this or outside the plane. Then this is simply just to merge all this data together, and it's basically a bunch of ORs to just get one value to decide if the sphere was inside the frustum or not. And at the end, we just merge this data together. And this is actually pretty much what we have in our code. This is actually a bit simplified, but pretty much how it works. Then, like I mentioned before, we have the SPU pipelining assembler called SPA that I made an implementation of as well to try to see if we could get any faster using SPA. For you that have been coding PS2 before, it's pretty much like VCL that was used for PS2 for the VU units, but this is for PS3 SPU. And it can give you that extra speed boost if you need it. The good thing about SPA is that it does software pipelining for you, so you don't actually need to unroll and your loops yourself, which is really convenient. In our case, it actually gives us a 35% speed boost using SPA. And the good thing about SPA is that it's actually not that different from using regular intrinsics, which is quite nice. And as you're coding assembly, and coding assembly is fun, we want to do that more, don't we? So looking at how the SPA in a loop actually looks like, this is just a bit of it. It looks quite similar to the intrinsic version. So it's really quite easy to move things over to SPA if you want it. And I can really recommend that you try it out if you need some extra speed. So this is how output can look like when you have implemented a loop in SPA. One thing to be aware of here is that you have an even pipe and an odd pipe description here. On the SPU, you can issue 2 instructions per cycle, and you have one even pipe and an odd pipe, and you want to maximize that as good as possible to have lots of instructions running in parallel. So in this example, there is actually 24 instructions per loop, meaning that it's 12 cycles to doing one sphere, which means it's 12. Actually, it only takes 12 cycles to do a full sphere, frustum versus sphere intersection test on the SPU in this loop, which is pretty fast. And this is actually the output you can get from SPA. I don't expect you to read this, but this is actually the output you can get. But you always write the code in a much more sort of high-level fashion, if you can call assembler high-level. But you don't need to actually do this manual pipelining when using SPA, which you would have to do if you just coded with intrinsics. So, moving on. Except for the new culling system that we implemented, we're also doing some additional culling. We are just not doing frustum versus sphere test, we're doing some more stuff as well. First thing is we do frustum versus axis line bounding box. Then we also project the axis line bounding box to screen space. And then we have our software occlusion, which I will detail a bit more. So, first, projecting the axis line bounding box to screen space basically means that we calculate a square area of the axis line bounding box for an object in screen space. And if the area is smaller than a specific setting on the object, we just skip it. And one can wonder why we just don't take the distance instead. That would be much, much easier. The problem is that in BF3 we have Wookiees and snipers laying out in the bushes and zooming across the level, meaning that field of view changes, so it just doesn't work to take distance. We actually need to do it like this to have it correct. Then we have our software occlusion. The software occlusion has been used in Frostbite for 3 years. It's a cross-platform. Must work on all platforms. And all our shipping games that we have shipped with Frostbite now, which is BC1, BC2, 1943, and Medal of Honor, uses Medal of Honor, the multiplayer part, uses the software occlusion. And the way it works is that artist makes occluders that we used to hide objects. And we also have the terrain generating and low resolution mesh as well that we are using. So why do we actually use software occlusion? We want to remove CPU usage and not just GPU time, meaning that we want to cull as early as possible in the frame. One might suggest that you should use GPU queries, but the problem for us is that the GPU is always lagging behind, and we want to cull as early as possible. And if you want to use the GPU, well, you're lagging behind, and you can't just use it for the CPU work that we want to do. And another really important thing for us is that it must support destruction, meaning it must be easy for us to remove parts of a house, for example, if it gets destroyed. But we still want to have occlusion on the entire house, but we must have the support to easily remove things from it. And that's really important as well. And another thing that's good as well is that it's easy for artists to control this, to build the occluders that they want. So how does the software occlusion actually work? It's really simple. We render piece one style geometry to a C buffer using software rendering. And software rendering is your typical scanline-based software rasterizer that you wrote long ago when you didn't have any GPUs. So that's pretty much what we use. It's really simple. And our target buffer is a 256 by 114 floating point C buffer. So it's pretty low res, but it works really good for us. So to actually do this, we have a bunch of different steps. So first we have an occluder triangle setup step, as well as a terrain triangle setup step. Then when those are finished, we need to rasterize those triangles that the first part has outputted. And then when we have rasterized those, we use that in the culling. We use the C buffer that has been rasterized. So if you look at how the occluders may actually look like, this is a high-res rendering of the occluders. And this is how it actually can look like in the game. And if you look at a screenshot from the game, this is how it looks in-game. So if we overlay the occlusion C buffer in its actual resolution, it sort of looks like this. So this is how it looks. It's fairly, as you can see, it's quite low res, but it works quite well for us as well anyway. So how do we actually schedule this? First, we run a bunch of occluder jobs that processes the triangles of all the occluders. As well, we have one job that just generates the triangles from the terrain. The next phase is just to rasterize those triangles into the C buffer. Then, after that, we uses this in the culling and do a C buffer test against the C buffer, and to reduce, even further reduce the number of objects that we want to draw. So looking at how it actually works. So this is a quite simple example. First we have one job that checks if this star is inside. Yeah, it's inside. Then we simply just project those triangles to an output buffer which has lots of triangles in it that's being waited for rasterization. Then check this one. Yeah, it's inside. Simple. This one is actually intersecting the frustum. Then we need to do a full clip on it to actually do all clipping against the frustum and insert those triangles into the output stream as well. And this case, the sphere is just outside. And the output is a bunch of triangles. So next step is to do the actual rasterization of the triangles. And the way it works is that we set up a number of jobs. In this case, it's just 2 jobs to just simplify how it looks. Each job has its own C buffer because it makes scaling much better. So when we start rasterizing, the first job takes 16 triangles of the output buffer, which has been generated by the jobs before it, rasterizes those. The next job simply takes the next 16 triangles, rasterizes those, and then when the first job has finished, it takes the next 16 triangles, and so on. And when this has finished, we run one step, and that just merges these C buffers. And the good thing about doing it like this is that we get really good scaling. If we will do it in a more tiled way fashion, it will mean that one job might be really heavily overloaded with triangles, while another one won't have any triangles at all, depending on how the scene looks like. Having it like this, it scales really well, and then the merge pass in the end is really fast, so that's never a problem really. Then we actually need to use this C buffer for something. So here's how we do our C buffer testing. We simply calculate the screen area of an object again, just project it down to screen space. Then we take the minimum distance value from the camera, which is 1 C value. This single C value is used when testing against the C buffer. So the way it works is pretty much having it like this. If you have the C buffer that I showed before, then we have one object that is here. It will be visible, so that's not a problem. It will be drawn as usually. Same for this one. And then if we add another one here, it won't be visible at all. So we just will skip that if it's behind the C buffer. Same here and same here. So that's pretty much how the occlusion buffer is working, or our occlusion system. So if you can draw some conclusions based on all this, is that for us, high-performance culling is really important. Our worlds are really dynamic. We have lots of stuff in them. And especially in BF3, we try to scale up things even further. And it's really important for us to have more stuff, but still have reduce the complexity of everything. Another thing that's really important for us when doing culling as well is to not reduce just the GPU time, but even reduce the setup time for all our rendering systems. So we spend a bit more of time to just do some quite detailed culling, but in the end it really saves us performance. And really takeaway about the new culling system, it's it's all about designing simple data. Just doing a really simple data layout for us works really well. And this is pretty much what we use for the new Culling system. Another thing that's to take away from this as well is that simple data often means simple code, and this is really true in our case. We now use a really simple data structure, and the code got really simple, and it's easy for us to optimize it even further if we want. And when doing things like this is really important to understand your target hardware. Look at how the instruction set, how the caches works, or branches heavy, things like that, before deciding on when implementing a new system like this. In our case, the PS3 360 and multi-core PC is quite similar actually, so our system works quite well on all these systems. And I also would like to take a chance to just thank some of these people that helped me out with the presentation, giving feedback and things like that. So, any questions? No questions?
Yes.
All right.
Hi, I got a question based on an assumption. I guess that you have a physics engine which does not use brute force as calculations, or probably have special partitioning, BVH, octree, something like that. Why don't you use the same special partitioning from your physics engine to do your calling?
Well, we're using Havoc actually for our physics engine, so this is,
Not possible?
Yeah, well, it might be possible, but it's not something that we actually looked into. So this is just for scaling the more of a rendering system. So. Also, just to mention, if you could fill out those forms, it would be really helpful for me to get a feedback from you guys.
I have one question. Can you talk a little bit about how you added objects into your entity grid a little bit more? You mentioned that you did an interlocked increment to allocate a new block from an entity grid. Did you always allocate an entire new block to add a new object, or could you add objects to a block?
No, that's a good point. When we have allocated a new block, we simply just increase count for the block. And, if the block isn't full, we just insert it into that block. And if the block is full, we just allocate a new one. No more questions? All right. Thank you.